All right, for stoichiometry examples, I'm going to skip right to example 2. So hopefully you've already gone through example 1 on your own. In this example, we have a photosynthetic reaction that may be written in the form ACO2 plus BNO3 minus plus CHPO4 minus plus DH plus EH2O goes to basically biomass plus FO2. Okay, so let's do some counting. We've got 1, 2, 3, 4, 5, 6 unknowns. But now, well, let's write that down. 6 unknowns. And in general, what we try to do is balance each individual element, right? So we've got carbon, oxygen, nitrogen, hydrogen, phosphorus. And I believe that's all. Yep. So 1, 2, 3, 4, 5 elements. So if we tried to solve this problem just by balancing conservation of mass of the elements, we'd only have 5 equations, even though we have 6 unknowns. So this tells us that we need one other equation. And this is when we need to rely on that second part of the principle of stoichiometry. So a chemical reaction must conserve the number of atoms for each element and the electrical charge associated with ions. So in our first example, we didn't really have a change in charge, so we didn't have to worry about that. In this example, we've got negatives and positives going over to neutral on this side. So this tells us we need to balance charge as well. Okay, so let's write out our equations. All right, let's start with carbon. So the only carbon that shows up on the left-hand side of the equation is right here in our carbon dioxide. And the coefficient there is just A. And the only place carbon shows up on the right-hand side is in our biomass. So we know that A has to equal 106. That's how we get an equal number of carbons on the left-hand side as the right-hand side. Okay, so that tells us A pretty quickly. All right, now let's keep it moving. Let's do oxygen. Okay, so we've got a coefficient A here, but there's 2 oxygens in carbon dioxide, so we're going to have 2A. We've got another 3 oxygens times B over here, so that's going to be plus 3B. We've got 4 times C oxygens here. We've got 1 times E oxygens here. And that's all for the left-hand side. On the right-hand side, we've got 110 oxygens in our biomass and 2F in our oxygen waste product. So that's going to be 110 plus 2F. Okay, so can't do much more with that right now, but let's move on to nitrogen. All right, we've got B nitrogen here. And that's the only place it shows up on the left-hand side. On the right-hand side, nitrogen only shows up in our biomass. So again, we get our coefficient B immediately. It has to be 16 in order to have the same number of nitrogen elements on either side of the equation. All right, let's see, what's next? Let's do hydrogen. Okay. So we've got C hydrogen over here, D hydrogen here, 2E hydrogen here. So that's going to look like C plus D plus 2E. And the only place hydrogen shows up is in our biomass. So C plus D plus 2E has to equal 263. All right, we've got one more element to check. That's phosphorus. So we've got C phosphorus here, and the only place it shows up over here is in our biomass. So right away, we also get that C has to equal 1. Okay, so what looked pretty nasty at about this step is now looking much more manageable, right? We already have A, B, and C, so actually our only two unknowns at this point are E, F, and D. Sorry, I think I said 2, but we have 3 unknowns. Okay, so 3 unknowns left, 2 equations, but remember we haven't balanced charge yet. So now we have to look at charge. Okay, so in front of this coefficient, or in front of our nitrate ion, we've got B. And this ion has a single negative charge. So that means we're going to multiply -1 times B. That's our net charge of nitrate, NO3-. So then in order to balance charge, which I'm just going to represent by a plus or minus sign, we've got a negative B charge from our nitrate. Over here, we've got a -2 charge that's multiplied by C. So that's going to be a -2C charge. And then last but not least, on this side, we have a positive hydrogen ion over here that's multiplied by D. So that's going to be plus D. And that's all on the left-hand side. And as you can notice, we have a neutral charge on this side, so neither of these have a plus or a minus in front or behind them. So that means that this has to equal 0. Okay. So here's our only unknown in this equation. So now we have 3 unknowns. We've got 3 equations to solve them. I'm not going to go through that algebra because I'm just going to plug it into the computer. And what you find is, I'm running out of space, but we'll write it over here. Let's see, how do I want to write it? So we'll say D, this has to be 18. E has to be 122. And F has to be 138. So again, if you're doing this in your homework, you would just plug these equations into the computer and have the computer solve it for you. That's what I would expect you to do in this class. In an exam setting, I would give you something that would be much more manageable to do on pen and paper with a calculator. Okay, so just to round this all out, we will plug in these coefficients so we can get a balanced equation. So this is going to be equal to 106 CO2 plus 16 NO3 minus plus 1 HPO4 2 minus plus 18H plus 122 H2O goes to C106 H263 O110 N16 P1 plus 138 O2. So here's our final balanced equation. All photosynthetic reactions can be written more or less like this. And again, this CHO and P, that's basically our biomass. So all biomass can be some variation of this. This ratio of 16 nitrogen to 1 phosphorus is actually really important. It's called the Redfield ratio. But I'm rambling, so I'm going to stop there before I go too deep into the Redfield ratio, and we'll call it good.